All right, so we come to our second best paper candidate from Sydney. Niruth will present his work entitled Passive Identification of Wi-Fi Devices at Scale, a Data-Driven Approach. Please welcome the speaker.
Hey, good morning. I'm Niruth, and I'll be presenting my work on passive identification of Wi-Fi devices at scale. So to start off with, I'm just going to give an introduction to Wi-Fi and how it's pretty much integrated in all our lives, Right now, everyone has a smartphone, laptop, and it's probably connected to the internet. But it's not just limited to our phones and our laptops. It's pretty much in every IoT device. From our security cameras to our coffee makers, they probably connect. With this integral connection, we get one major problem. How do we identify the different devices that connect to a network? And can we say which device is which? And that's exactly what our research plans on answering. We developed a method that can passively identify the different devices that connect into a network. Now, before I get into the technical parts of how we accomplish this, I'm just going to give a scenario in which this research can be useful. So let's break it down into 4 potential scenarios. One is to deduce the socioeconomic backgrounds in a neighborhood. So say you've got a neighborhood and you want to identify where public infrastructure needs to be built. One way of doing this is to figure out what kind of devices are being used in different regions of a neighborhood. So say you got an area with a lot of high-end new devices, it's easy to, you could make an assumption being like, okay, you get a lot of, you get a high economic background there. While where you get devices which are older or tend to be more diverse, you could say you got a more diverse economic background there. And this can be used by public services to figure out where infrastructure needs to be built and what kind of services can be implemented to different regions. Another thing is for your ISP. So say you got 2 separate households. One household, you got a lot of gaming consoles, you got smart TVs, and you got a lot of laptops running in. A household like that needs high-end, high bandwidth internet. While if you have a lab with, say, a bunch of thermostats and smart lighting, you need a stable connection, but you don't need very high speeds. So this allows ISP to figure out, okay, what connection I should give to different areas, and can we cater our services according to the needs that are required. Another thing is a neighborhood device audit. So let's look at this in terms of security. Say you run a device audit around a certain region and you figure out what security cameras or what houses have security cameras installed in it. You could figure out areas where there are high private security and regions where there's low private security. So law enforcement could use this to figure out where we should put more public security services or public cameras to make a neighborhood safer, or to see what areas are more vulnerable to an attack. And the final thing is selective marketing. So brands could figure out where we have a higher use case of Apple devices versus Samsung devices to target the advertisements to make it more efficient to build up. So there are 2 ways you could do device identification, active and passive. We focus on passive for a few reasons. One reason is active tends to be quite intrusive. You're sending requests to a device, asking it information, which can interrupt flows and also disrupts the device's normal behavior. Also, you need, not every device will respond. Only certain devices will respond to the active probe sent, which limits your reach. And you also need permission by either network administration to join into the network, or you need to hack into it, which raises ethical considerations. So we focus on a passive approach, because in passive, we just monitor the network traffic flowing about. We're not intrusively sending requests to any devices. We're not requesting to connect to any devices. We're just observing everything around us. So this prevents the limited reach approach. We don't need permission to join. We don't need to be connected to any specific network. We just observe everything around us, and we use that information to see if we can detect the different devices. So the previous work in this field focuses on using specific device features such as MAC addresses or universal unique device identifiers to create physical fingerprints, or use temporal features like probe request patterns or packet interarrival time to see if we could leverage device communication features or timing features to differentiate which device is which, or to identify, okay, we got two separate phones. Phone A sends packets X amount of times in a minute, and packet B sends it, so phone B sends it Y amounts of times in a minute. Could we use this to fingerprint the different devices? And the other one was looking at frame associations. So the idea there is you'll observe these features over a long period of time and see, could we use the behavior of a device to identify them? In theory, they sound really good, but they have a few practical limitations. One is lack of stable features. If you use features like MAC or UUDIEs, which no longer are available, and for MAC addresses, randomization. So MAC randomization will just fragment the data over time. So you can't get a full stream of data. You just get small fragments that change over time. The other thing is sampling variability. If you focus on time-related or the temporal aspects of data, what you need is series of data that's unbroken. In practice, it's hard to collect it over time. You get packet drops, you get devices disconnecting, which again fragments the data, which causes a problem of, okay, is this data fully representative of the device's behavior or the device's features? Third and fourth is scalability and explainability. So imagine you have a neural net, which some previous work I've done. You need a lot of data to train and retrain this model and adapt these models as newer devices come into the market. Also, it tends to be black box. They don't explain exactly how you get the output you're getting, so which makes you which makes you question the reliability of what's happening. So to overcome all of this, ideally you need a method that uses stable features, not fully dependent on temporal aspects of device behavior, can scale well with limited data, and you can explain exactly what's happening in your method. And that's what we have achieved. So I'm going to give you a quick overview of what we do, and then in the next following slides, I'll jump into the crux of it. So first we do is just capture network traffic. So we just use a Wi-Fi antenna and collect all data that's around us. Then we filter for probe request. I'll get into what a probe request is and why we chose it in just a second. So after we extract the probe request, we create a signature. And the final part of our method is matching these signatures against the database of known devices and determining the match probabilities. So now going into a probe request, what is a probe request and why do we choose probe requests? So a probe request is pretty much something your phone or your laptop or any device that uses Wi-Fi will send to your access point telling these are my device capabilities. It's also the way your phone tries to figure out what networks it can potentially connect into. So within this probe request, you get something called information elements, which specifies your phone's or your device's capabilities, everything from what rates it can support to what throughput it could handle. And this is used by the access point to determine how compatible is this device to join our network and can we create a stable connection through this. The reason we chose probe request is first, it's autonomous. It's sent by every device that enables Wi-Fi, and it's dependent on the device and not the network. The information it sends out is specific to your device. It doesn't matter what network's available or what the capabilities of network are. It's giving you information about your specific device, and also it has a lot of features that you can use and extract to figure out. So once we extracted the probe request, we extract these information elements and we create a signature. So we structured the signature as a dictionary. So here you could see two examples from our database. We're a Google Pixel 7 and a Samsung Galaxy A13. So here we take every attribute in the information element. So everything from supported rates, HD, extended, vendor specific, and we match it against a specific attribute value. So one thing I want to highlight here is if you look at the Google Pixel 7, you could see in vendor specific, you get two potential values here. And that depends on the device itself. So for example, if the device is in power saving mode or active usage, some of these attributes can change or have multiple attributes. And we want to make sure we are having a possible set of attributes that match all devices, or like all possible activities a device could be doing. So if it's power saving mode, or if it's in active usage, or if it's just on standby. So one thing I want to highlight here is by using probe request, we kind of achieve two of the things we set out to do. First, have something that has stable features and that can adapt to something variability that is not fully dependent on time. So over time, as protocols come and go, as newer devices come, we could be certain that probe requests will still exist as long as 802.11 exists, because you need that to connect into a network, and this gives stability to our method. So now I'll get into the crux of our method, and that's how do we match two signatures together to determine if it's the same device or if it's different devices. And for this, we have 3 steps. First, we calculate the similarity between all the attributes and attribute values. Then we compute the joint probability and we convert into weights. So here the idea is each attribute has a specific weight or a specific importance, and we want to identify for a given device which attributes we need to focus on and which attributes we do not need to. And instead of hard coding these values, we chose to do adaptive thing using probability, and I'll explain that in a bit. And then finally, we calculate weighted similarity. So going into the first part is calculating the similarities between all attributes. So we have 2 metrics for this, Jacquard and Hamming distance. So for all our ordered attributes like supported rates, HTR, extended supported rates, we use the Jacquard similarity, which calculates the overlap between a sequence, while the Hamming distance is for unordered attributes like HT, where you're looking at, it's like ordered attributes such as HT, where you're looking for a specific sequence of values. So as you can see here, for each, so given 2 signatures, we have a verification and target. We'll calculate the similarity either based on Jacquard or Hamming's for each attribute, and we'll get a score. So one thing to note here, in the target signature, you don't see an extended attribute. So there you're going to get a similarity of 0. So if 2 signatures have different numbers of attributes, that's not a problem. We'll just mark that similarity as 0 and we'll move on to the next. Then once we get these similarities, one thing we noted is that not all attributes have the same weighting when figuring out how similar 2 devices are. So what we came up with is a probabilistic method based on occurrence. So what we do is we take a sample of signatures, a sample of probe requests that's in the wild, and we'll calculate the probability of occurrence for each one. If you look here, the 2 examples shown here for the verification and the target signature, this is for supported rates. For these specific values, how often are you going to see it in the wild? You get 0.5 and 0.1. Now, individually, these values mean nothing. What we want to see is, can we figure out, can we get a weight for seeing both these values together? And for that, what we use a joint probability. So here you get 0.05. That means there's a 5% chance of seeing these 2 values together. And this helps us highlight, given 2 signatures, which attributes are more common, which attributes are more rare. And we want to focus on rarity, because that gives us a better saying of this is exclusive or this is specific to a particular device. So once we have this computer joint probability, we want to calculate a weight for it. So we need to transform it. You could use a plethora of functions to transform it, but there were 2 things we wanted to highlight when we are doing this. We want to give a higher weight for rare attributes, and we want to prevent bias. So to explain those 2, it means is, imagine when we are matching these 2 signatures, all the common values that you're going to see, for example, values like this, we want to lower its weight, and rare attributes or like or attributes where you'll see less often together, that's what we want to highlight and give a higher weight to. So the transformation we chose was this, and we use a lambda value of 2.1, which is a hyperparameter you could tune accordingly. We chose 2.1 because it gave the best results, and it found the best balance between our main 2 goals of wanting to highlight rare attributes and prevent bias between common attributes and rare attributes. Now, one thing to note, or going back to the previous note, what I said with the Google Pixel 7, you could have some attributes that can have multiple values. So if you look at extended supported rates here, you could see that in the verification signature, there are 2 potential sets of values, and you want to identify which value can occur into which extent. So what we do is when we create these verification signatures in our database, we also note down how often you'll see them in a particular signature. So imagine you look at extended supported rates here. For this value and this value, you get 2 separate occurrence probabilities, 0.78 and 0.22. That means for every signature we looked at, or for every particular verification signature we looked at, this value occurred 0.78% of the time, and this value occurred 0.2% of the time. The reason we account for this is we want to minimize penalties for less frequent combinations. So once you have the similarity, you have the weight, and you have the occurrence probability, it's just a matter of calculating a weighted average. And we get a match for every single device in our database. For example, here, this says, imagine our verification signature is Apple iPhone 14 Pro. Our target signature, or the signature we are matching, has a 0.99 probability. If you're comparing against Apple iPhone 13, we get a 0.9 probability, and so on for every device that we have in our database. And the beauty of this is you could always work it backwards from the match. You could work it backwards to figure out which attribute contributed to which value, and which attribute you need to focus on. What was the specialized, or what made this signature unique to be matched against a given device. So to evaluate our method, we collected probe requests across 50 devices. So here you could see each device, and you could see the number of probe requests that was collected for each device. And we used a Raspberry Pi and a Dell XPS with 3 alpha AWS antennas to collect all our probe requests. One thing I like to note is, compared to the previous studies in this field, we collected data 50 device, which tends to be quite larger, because the largest till this was 20 devices. And also this data is publicly available. So if anyone wants to use it, you're more than welcome to contact me, and I will give you access to a full database of probe requests for each device. So to compare our method, we used work by Gu et al., which used the neural net to do device classification based on probe requests. So we did a direct comparison with our method and the work proposed by Gu et al. Our method was able to get an accurate F1 score of 99% across our 50 devices. As you can see, we have almost perfect diagonal, which is 10% higher than what the deep learning methods were able to achieve. And where the most, talking about deep learning methods, where they failed or where they had the hardest time differentiating between devices were devices that were a generation behind. So imagine Apple iPhone 13 versus Apple iPhone 14, or a Google Pixel 7 versus Google Pixel 6. While these methods fail, our method was able to excel simply because we were focused on figuring out what makes this unique which attributes make this device unique versus what makes it more common, or which everything has, which gave us the advantage, and we were able to get a pretty high F1 score. But the main thing I want to highlight with our method is not its accuracy, it's its data requirement. So one experiment we ran was we took one probe frame per device we had, and we created the signature for it. And in the case of the neural net, we trained it, and we ran it across all the other to see how well we could do. So with just one probe frame, that's just one probe capture for a given device, we can get an accuracy of 92%, while a neural net gets somewhere around 10%. And as you increase it, you see they still get below 50%, while we are able to achieve 90+% and keep moving it up towards 99 as we increase our data requirements. So all we need to identify a device is just one probe frame that needs to be captured, and we could get results of 92%, which is one of the main things I want to highlight. The other thing I mentioned was, as you get different devices, the mode of the device affects your changes of probe frame. So what we did was we subset the data set according to active, passive, standby, and power saving standby, and we compared and checked our robustness. We were still able to achieve 99% accuracy against a device being power saving versus normal usage. So this helps us achieve all 4 of what we set out to be: that use stable features, adapt to sampling variability, give an explainable method that can scale well with data. So to summarize, I'll say we provide a real-time device identification system. We have a dashboard that you could run anytime, and we achieve high accuracy with very, very little data. Thank you very much.
All right. Time for questions. Do we have questions? Yes, that's the first one.
Thanks. Your motivation was also on the use of IoT devices like cameras and all these gadgets, where I would presume that the chipsets are more on the lower end of the available data rates and the capabilities. And so in your data set, as far as I could tell, there were only 3 devices from that class. Do you also have a larger data set that has these devices included? And can you comment on how accurately they can be identified from one another?
Yes, thank you for the question. So right now, our expansion of this is to expand our work towards IoT devices. That's like smart lights, security cameras, thermostats, and like even garden controls for temperature. And our accuracy is still maintained, and we will be publishing those results as we come.
Further questions? Yes.
Yeah, maybe a quick follow-up on this. Is this what you're doing? Is it a device classification or a Wi-Fi chipset classification?
It's a device type classification, and yes, the probe requests are more prone towards the specific chip or Wi-Fi chipset it's using. So one example I would use for that is, so imagine take Apple iPhone 13 and Apple iPhone 14, their Wi-Fi chipset's more or less the same, but it's the device's capabilities or the OS that runs makes differences in these attribute values that I mentioned. So for example, you have Apple iPhone 13 Pro or Apple iPhone 13 versus Apple iPhone 14 Pro and a 14. They have the same Wi-Fi chipset, but I can differentiate between Apple iPhone 14 being used versus Apple iPhone 14 Pro being used. And that can be attributed to small differences which we calculate.
Okay, but if you now go back to your IoT devices, as it was asked before, right? So then the variation of chipset is smaller. And even then, if you have a new version of these low budget devices, they sometimes even switch the Wi-Fi chipset because they got a cheaper offer from a different vendor. And then you have the same device and you want to detect the device, but the chipset changed. Wouldn't this mess up your detection?
That is a scenario that I have that could potentially something I definitely need to look into. Thank you for that.
Thank you. Further questions? Yes. We have a question here. Oh, that was close.
So I want to ask about the effect of when you don't receive the probe request.
So every
Errors.
device that has Wi-Fi enabled will send a probe request. So you could be connected to a network and it's still going to send probe request telling it this is the information that's available, just the idea of maintaining, can I maintain this connection or is there a better connection I can connect to? So the idea of not being able to collect probe requests would only be viable if your Wi-Fi is off or your device is not using Wi-Fi at all. So as long as Wi-Fi is enabled, there's probe frames come in every couple of seconds. So it's very easy to capture that.
Right. Last question.
How about the effect of Wi-Fi versions?
So as I said, in probe request, the actual Wi-Fi doesn't matter, right? What matters is it tells your device's capabilities in the program. So you could be using Wi-Fi 6, Wi-Fi 5, Wi-Fi 4. The probe request that's going to be sent is more or less going to be the same, and it's going to give you information about your device. So the network conditions won't matter.
All right. Thank you. And
Thank you.
Thank the speaker again.